Have you ever wondered how molecules, the building blocks of everything, rearrange themselves? Picture this. The molecules in our universe are constantly on the move, shifting and rearranging themselves like dancers on a stage. This process is known as molecular rearrangement, a fascinating aspect of chemistry that allows for the transformation of molecules into new substances. At the heart of these rearrangements are electron-deficient systems. These are molecules that are quite literally short of electrons. These electron-hungry molecules tend to be highly reactive, always on the hunt for other atoms or molecules to bond with, to satisfy their electron cravings. But where do these migrating electrons go, you might ask? Well, they typically find new homes with atoms of oxygen, nitrogen, and carbon. These atoms are like welcoming hosts, opening their electronic doors to incoming guests. The result is a reshuffling of the molecular structure, a rearrangement that leads to new compounds with different properties. Consider an oxygen molecule, for instance. It's more than happy to welcome an extra electron into its fold, resulting in a negatively charged ion. The same goes for nitrogen and carbon atoms. In fact, these atoms are often the very ones that electron-deficient molecules seek out, leading to an intricate dance of electron movement and molecular rearrangement. This dance is not random, however. It's a meticulously choreographed routine, dictated by the laws of chemistry. Each atom knows its role, each electron knows where to go. It's a symphony of movement at the molecular level, a ballet of bonds being broken and formed. This is just the tip of the iceberg when it comes to molecular rearrangements. There's a whole world of complex reactions and transformations out there, from Baeyer-Villiger and Dakin oxidations to Wagner Meerwein rearrangements, from Pinacol-Pinacolone rearrangements to the dances of electron-rich systems. Just like a dance, molecules know when and how to move. Fascinating, isn't it? So let's dive deeper into this captivating world of molecular rearrangement. Stay tuned, there's so much more to explore. Now let's delve into the intricacies of Baeyer-Villiger and Dakin oxidations. In the realm of molecular rearrangement, Baeyer-Villiger and Dakin oxidations play a pivotal role. They are the unseen masters, directing the flow of electrons with finesse, precision, and a hint of mystery. Let's begin with Baeyer-Villiger oxidation. It's a fascinating process, involving the addition of an oxygen atom to a carbon-carbon bond. This results in the formation of an ester from a ketone or a carboxylic acid from a cyclic ketone. The reaction proceeds through a three-step mechanism. The first step is the formation of a peroxyacid, which then forms a Crigi intermediate. The final step is the migration of an alkyl or aryl group, leading to the formation of the ester or carboxylic acid. The beauty of this oxidation lies in its stereochemistry, as the migrating group retains its configuration. Moving on to Dakin oxidation. This reaction involves the conversion of an aryl aldehyde or aryl ketone into a corresponding phenol. The reaction proceeds through a two-step mechanism. The first step is the formation of a hydroperoxide intermediate. The second step is the thermal decomposition of this intermediate, resulting in the formation of the phenol. The Dakin oxidation is a symphony of electrons, with each step carefully orchestrated to create a beautiful molecular masterpiece. However, it's important to note that the Baeyer-Villiger and Dakin oxidations are not just abstract concepts. They have practical applications in the synthesis of pharmaceuticals and fine chemicals. For example, the Baeyer-Villiger oxidation is used in the synthesis of certain antibiotics, while the Dakin oxidation plays a role in the synthesis of certain anti-inflammatory drugs. These oxidations are like the choreographers of the molecular dance. They guide the electrons, ensuring each move is executed with precision and grace. They create a harmony of atoms and bonds, a symphony of chemical reactions, a dance of molecules. And in this dance, every step, every turn, every leap is a testament to the beauty and complexity of chemistry. Let's journey further into the world of rearrangements with Wagner Meerwein, Pinacol-Pinacolone, and others. Imagine being a molecule, and suddenly, you find your atoms rearranged to form an entirely different structure. This is exactly what happens in a Wagner-Meerwein rearrangement. Named after two brilliant chemists, this process involves the movement of a hydrogen, alkyl, or aryl group from one carbon atom to another within the same molecule. This migration involves a carbocation intermediate, and the rearrangement allows the molecule to stabilize this high-energy intermediate. It's like a molecular game of musical chairs. Next up, we have the Pinacol-Pinacolone rearrangement, a classic example of a 1,2 rearrangement. This reaction starts with a diol, also known as pinacol, which is converted into a ketone, the pinacolone, using an acid catalyst. The reaction is fascinating because it involves the migration of a methyl group and the simultaneous loss of water, leading to a dramatic change in the molecule's structure. But the rearrangement party doesn't stop there. We also have the Beckmann, Curtius, Lawson, Hofmann, and Schmidt rearrangements. These reactions involve the migration of atoms or groups to form isocyanates, isocyanic acid, and nitrogen gas, among other products. Each reaction has its unique mechanism and stereochemistry, and together they highlight the versatility of molecular rearrangements. The Beckmann rearrangement, for instance, transforms oximes into amides under acidic conditions, while the Curtius rearrangement converts acyl azides into isocyanates. The Lawson rearrangement involves the transformation of hydroxamic acids into isocyanates, while the Hofmann rearrangement converts primary amides into primary amines. Finally, the Schmidt reaction involves the migration of a hydride or alkyl group from carbon to nitrogen in a molecule. These rearrangements show us the endless possibilities in the world of molecules. They illustrate how seemingly small changes can have a profound impact on a molecule's structure and properties, and they remind us of the dynamic and ever-changing nature of the molecular world. So let's continue to explore, learn, and marvel at these remarkable molecular transformations. Now, let's switch gears and explore the rearrangements of electron-rich systems. In the realm of molecular rearrangements, electron-rich systems are the prima ballerinas, dancing with grace and precision. One such fascinating dance is the Stevens rearrangement, a name reaction in organic chemistry involving the migration of an alkyl group in an amine oxide. This rearrangement is particularly interesting because it allows for a wider variety of products, depending on the alkyl group involved. Next on our dance card is the Somlet rearrangement. This one is a bit of a showstopper, involving a reactant that is an N-alkyl N-methoxyamine. The rearrangement results in an aldehyde or ketone, with the process being a valuable tool in the synthesis of complex organic compounds. Then there's the Favorsky rearrangement, which involves the transformation of an A-haloketone into a carboxylic acid with a smaller carbon skeleton. This rearrangement is known for its elegance, as it involves a cyclic transition state leading to a predictable product. The Neber rearrangement, on the other hand, is a bit of a dark horse. It involves a one-pot transformation of an oxime ether into an A-aminoketone. The Neber rearrangement is a versatile and useful method in the synthesis of a wide variety of complex organic molecules. Finally, the benzylic acid rearrangement takes center stage. This rearrangement involves a 1,2 rearrangement of 1,2-diketones to A-hydroxy carboxylic acids using base. The benzylic acid rearrangement is a classic example of a reaction that can be explained with a pericyclic mechanism. Through these dances of electrons, we see a rich and complex choreography unfolding. Each rearrangement, each step, each move is a testament to the intricate beauty of molecular transformations. These rearrangements not only allow us to create new and complex compounds, but also offer us a deeper understanding of the fundamental principles of chemistry. Electron-rich systems truly add a twist to the molecular ballet. Next, we'll see how rearrangement leads to an aromatic nucleus with Fries and Claisen. In the realm of molecular rearrangements, the Fries and Claisen rearrangements are particularly intriguing. Named after their discoverers, both of these reactions involve the movement of an acyl group in a molecule to a new position, leading to the formation of an aromatic nucleus. Starting with the Fries rearrangement, it's a process that takes an ester and, under the influence of heat or a Lewis acid, rearranges it into a ketone or an alcohol. This rearrangement happens when an acyl group shifts from the oxygen of an ester to the neighboring aromatic ring. It's like a molecular game of musical chairs, with the acyl group finding a new seat on the ring. On the other hand, the Claisen rearrangement is a classic reaction that involves the sigmatropic rearrangement of an allyl vinyl ether to produce a GD unsaturated carbonyl compound. It's a thermal concerted process that beautifully illustrates the power and precision of organic chemistry. But the magic doesn't stop there. Let's now delve into the realm of pericyclic reactions. These reactions, which include electrocyclic, cycloaddition, and sigmatropic reactions, are a fascinating group of organic reactions that occur in a single step, without any intermediates, and involve a cyclic redistribution of bonding electrons. Take the Cope rearrangement, for instance, a classic example of a sigmatropic reaction. It's an internal process where a molecule undergoes a structural rearrangement. Specifically, it's a rearrangement, meaning 3 atoms on one part of the molecule swap places with 3 atoms on another part, all in a concerted, seamless dance. From Fries and Amp Claisen to pericyclic reactions, the world of molecular rearrangement never ceases to amaze. It's a captivating journey that takes us from the rearrangement of electron-deficient systems to the intricate dance of electron-rich ones, illustrating the awe-inspiring complexity and beauty of organic chemistry.